Dear students, welcome back. See, as we have seen the multiplication algorithm in the last class for the data is represented in sign magnitude form. We will continue with the multiplication algorithm. So there is another important algorithm. So this algorithm is very important in the exam point of view. So please pay attention. So this algorithm is called Booth algorithm, right? So Booth multiplier. So Booth algorithm. So when we use this algorithm, so this algorithm is used for multiplication of two numbers, right? So these two numbers are sign numbers. So for example, right, so I want to multiply a number like minus 9 into minus 13. So the two sign numbers, right? So these numbers initially they are represented in 2's complement form. So how to represent minus 9 in 2's complement form? For example, here I am using 5-bit as in the last example I am using 5-bit precision, right? So if I use 5 bits, so how to represent minus 9? So first I represent plus 9, right? So how to represent plus 9? So 0, okay, 1 0, okay, 0 1. So to represent, this is a plus 9 represented in 5 bits. So if you want to represent minus 9, you need to take 2's complement of it, right? How to take 2's complement? Just take first write 1 here. So then you take the 1's complement. So 1 1 0 1. So this is the representation of minus 9 in 2's complement form. Similarly, minus 13, right? So plus 13 is represented as 0 8 4 1 1 0 1, right? Similarly, you can represent minus 13 by taking 2's complement, right? 1, right? You can take 1 0 0, right? 1. So this is minus 13. So if the numbers are represented in 2's complement form like this, right? How to perform multiplication, right? Using a Booth algorithm, using Booth algorithm, right? So that is the agenda, right? You can see here minus 9 into minus 13 is plus 117. This is the expected result. So let us see. So same rules applicable here. So I am multiplying here 5 bit into 5 bit, okay, 5 bit number into 5 bit number. I am getting a 10 bit result, right? So 10 bit result. So first accordingly let us investigate what is the hardware for this. Then we go for the then we go for the algorithm. Then we go for the same problem, right? Now this is the hardware. So you can observe here 2's complement here. So first of all we want to multiply two numbers, right? As I told, I want to multiply two numbers. For example, minus 9 is represented with 1 0 1 1 in 2's complement form. So minus 13 is represented as 1 0 0 1 1. Suppose minus 9, let me call it as a multiplicand, you know, right? In same, right? In multiplication, multiplicand. Another one is a multiplier, right? Multiplier. So let me show you what I need to do. So this multiplicand in the previous case I put in the BR register. So let me assume for this example BR all registers are 5 bit, right? So BR, okay. So what is the role of BR register? To store the multiplicand. So I am storing the multiplicand. So I am writing here. So okay, 1 1 1. Similarly, AC is initialized with 0 initially, right? So similarly QR I hold the multiplier, right? So 1 0 0 1 1. Listen Babu, here the important thing is I have one more extra bit called Qn plus 1, right? So in this case, this previously I am monitoring only this MSB bit, right? Sorry, this LSB bit, right? Always I am monitoring this LSB bit to take the decision, right? So for example, first I monitor this bit, right? So this is the Qn first initially, then in the second iteration this becomes the Qn, like that, right? So in the third iteration, this fourth iteration, fifth, like that I am once I shift right, this will come here like that, right? Now in case of Booth algorithm, what is the extra thing is I need to monitor the 2 bits with the initial Qn plus 1 will be initialized with 0, right? That is the case, okay. So initially Qn plus 1 is initialized with 0. Now to take the decision I need to monitor the 2 bits Qn and Qn plus 1, right? Okay, this is the important thing, okay, you need to understand. So what I told, so this is I have a complementer and parallel ladder. What it can do, so it can perform AC, okay. So it can perform AC plus BR, you know the perform complementer what it can do, AC plus BR, and the result is stored in AC, right. This is one thing it can do, and another thing what it can do, it can perform AC plus BR bar plus 1, right. So this thing also it can do, right. This so similarly this is the role of complementer, and parallel adder can do this 2 micro operations. Similarly, what is the role of sequence counter? Always it will be decrement. So initially I need to store how many times I need to iterate this multiplication process, so that count I will, this is a kind of iterator variable. In the software it acts like a iterator variable. In the hardware we have a sequence counter, we initialize the sequence counter with how many times we need to repeat this process, okay. So that is equal to number of bits in the multiplier, like here we are using 5 bits, so the sequence counter is initialized with 5, okay. So let us go for the algorithm. I hope you understand the hardware. So one more time I am repeating here. So what is the hardware? So AC is initialized with zeros, QR is initialized with the multiplier, right. So BR is initialized with the multiplicand, sequence counter is initialized with the how many times I need to multiply. Similarly, I have one extra bit called Qn plus 1, this bit is initialized with 0, right. So having understood this, let us go for the algorithm. So this is a simple algorithm for both multiplier. So having initialized this, right, so we have a multiplicand in BR, multiplier in QR, right. So this is an initialization step, just now I told, right. AC initialized with 0, Qn plus 1 initialized with 0, Sn is initialized with n. So n times we need to repeat this process, right. Sequence counter is initialized with n, n is nothing but 5 here. In this example I am taking 5 bits, right, number of bits, n is nothing but number of bits of the multiplier, right. Now what I need to monitor? I need to monitor the two things, right. So Qn and Qn plus 1, both I need to monitor. So if these 2 bits are 0, 1, right, for example Qn equal to 0, what is the meaning of this? Qn equal to 0, Qn plus 1 equal to 1. If this is the case, what I need to do? I need to perform addition and shift, right. So what shift I need to do? So carefully here, previously I am performing the shift, so here also I am performing right shift. Previously I am performing, in the previous algorithm I am performing the right shift, here also I am performing the right shift, but careful here you are performing the arithmetic right shift. So I told that arithmetic, okay, arithmetic right shift. So what is arithmetic right shift, right. So okay, I told that I'll explain this later, so hold on this. So first see the algorithm, right. So if Qn equal to 0, Qn then perform addition and right shift, right. Similarly if Qn equal to 0, sorry, if Qn equal to 1 and Qn plus 1 equal to 0, so 1 0, if you get 1 0 combination, then you need to perform subtraction and right shift. So what is subtraction? You want to perform AC minus BR and the result is stored in AC. So instead of AC minus BR, what you can perform? AC plus BR bar plus 1 and AC. So first perform the subtraction, then shifting, right. So these are the two cases. So other two cases may be 0 0 or 1 1. In these two cases directly you can perform right shift, right. So this thing you need to repeat till the sequence counter not equal to 0. So if sequence counter equal to 0, just end the algorithm, right. Understood, right. So what you need to take? Very simple algorithm. So if you need to monitor the 2 bits Qn and Qn plus 1, if these two are 0 0 or 1 1, directly perform arithmetic right shift. If these 2 bits are 0 1, addition and right shift. If these 2 bits are 1 0, subtraction and right shift, that's it, right. So what is arithmetic right shift? So I told that there are 3 kinds of shifts are there in a, okay. For unsigned numbers we have a logical shift, for signed numbers we always have a arithmetic shift, okay. So for example here, for example I take for example 5 bit number, right. So if you perform, for example this 5 bit number is 1, okay, 0 1 0 1, right. So for example in the previous case we did a logical right shift. So what is logical right shift? So in case of logical right shift, what happens? So in this case, okay, so this new bit here will get a 0, right. So here this bit will come here. So here the new bit will be 0, this bit will be, okay, let me draw the 4 5, right. So this bit will come here, this bit will come here 0, this bit will come here, right. So this bit will come here, so this bit will come here, this bit will come here, this bit will come here, this bit will be exit, right? That will be lost, we lose this bit, right? So this is a logical right shift. But what is arithmetic right shift? So in case of arithmetic right shift, this is for signed numbers, right? So in case of arithmetic right shift, what we do is, so 1 0 1 0 1, right? So we retain the sign bit as it is, right? We retain the sign bit as it is, then perform shift, right? So the intention is we should not, so this will be gone, right? So 1 we retain, so then 1 here will get a 1, right? This 0 will come here, this 1 will come here, this 0 will come here. So this is what the arithmetic right shift, Babu. So while performing the Booth algorithm, you need to do this arithmetic right shift, okay? So please remember this point, okay? So then we proceed with the example, right? So for example, here I want to solve the two numbers, right? So I told that minus 9 into minus 13, right? So let me draw this, right? So I have a qn plus 1, right? So qn plus 1, okay? Similarly AC, right? QR, AC QR, right? Similarly qn plus 1, right? So okay, here again I am writing for clarity. So we have QR qn plus 1, right? So then okay, let me write here. So this qn plus 1, write in the close to this, okay, qn plus 1. Then we have a sequence counter. So right, so qn is initialized with 0, qn plus 1 is initialized with 0, qr is initialized with the, okay, qr is initialized with the multiplier, right? What is a multiplier here? 1 0 minus 13, right? 1 0 0 1 1. This is a multiplier here, right? Similarly AC is initialized with 0, right? Similarly BR is initialized with what, right? Multiplicand. What is multiplicand here? 1 0 minus 9 1 1. So we also want to do, right, subtraction, right? For that I require a BR plus 1, right? So BR bar plus 1, just take 2's complement of this, right? So what will get? 1 0 0 1 0, right? This is BR plus 1, just write for calculation, it will become easy, right? Now let us start the first iteration, right? So in the first iteration, what you need to monitor always, okay, sequence counter is initialized with 5, right? So it is initialized with 5, 5 is nothing but 1 0 1, right? Now in the first iteration, just monitor this bit and this bit, right? So this bit is 1, this bit is 0. Then what addition you need to make? This is the initialization, let me put this, right? So 1 0, what is the thing? You need to perform AC minus subtraction and shift, right? This addition you need to take, you need to perform subtraction and shifting, right? So subtraction you are doing like this, right? BR plus 1 and AC, and second step is you need to perform right shift. So arithmetic right shift, arithmetic shift right operation, right? Now do this. So take AC minus BR. So AC is 0 0 0 0 0. What is BR bar plus 1? 0 1. So this is BR plus 1, right? So that's why I have calculated okay, in prior. So just perform addition, 1 0 0, right? 1 0. Then QR will be 1 0 0 1 1, qn plus 1 will be 0, right? Then perform what? Perform the arithmetic right shift. See, this is the first step. So second step, what you need to do? Arithmetic right shift. What is arithmetic right shift? So this sign you retain as it is, then this 0 go here, 1 come here, this 0 come here, 0 1 1 0 0 1, this 1 will go here, right? So this is the first iteration we have completed. In this first iteration, this is the whatever the partial product we obtained. So also we decrement the count to 4, right? This is the partial product we obtained in the first iteration, right? Now similarly in the second iteration, again what? You need to look into this 2 bits, qn and qn plus 1. If these 2 bits are 1 1, so 1 1 means what is your addition? Just perform the, only one step you need to do, just perform the arithmetic right shifter. So you take this number, perform the arithmetic right shifter, right? So do the shift for this, what happens? So this this sign will be retained here, right? 0 0 1 0 0 1 1 0, right? So this 0 will go here, this 0 will go here, this 1 will come here, right? So 0 0 0 1 0 0 1 1 0 0 1, right? Now this is the thing, second iteration, right? Again in the third iteration again what we need to do, just we need to monitor these two bits 0 1. So 0 1, these two bits are 0 1. So what here in this case I need to do addition and shift, right? So AC plus BR and the result is stored in AC, and the second step is arithmetic shift right, right? So just do the addition. What is addition? 0 0 0 1 0. So this is what, right? And you need to add with a BR. So BR is nothing but 1 0 1 1 1, right? So 1 0 carry 1 0 carry 1 1, right? So 1 1 0 0 1, right? You write this, right? 0 0 1 0. So 0 1 1 0 0 1. This is what, right? Then perform the shift right. This is the first step, the addition step. Second step is shift right. So here take care that you need to retain the sign here 1, then you shift 1 1 1 0 0, right? 1 0, right? 1 1 0 0. So this is what, right? 1 1 1 0 0 1 0 1 1 0, right? Similarly here the count become 3, here the count become 2, right? So this is the third iteration. So in the fourth iteration what, again you need to monitor these two bits 0 0, right? So let me take one more slide here. So in the fourth iteration, so let me write the previous outcome. So previous outcome in the, right, previous outcome is I got 1 1 1, right? 0 0, right? 1 0 1 1 0 0, right? So this is the contents of AC, okay? This is the contents of QR, and this is Qn plus 1, right? So in this case I got 2 zeros. So what addition in the fourth iteration I need to make, just perform arithmetic shift right, right? How to perform arithmetic shift right? Just put 1 asterisk 1, then perform the shift 1 1 1 0 0 1 0 1 1, this 0 will come here, right? So similarly count will become 1, right? So similarly this is the final case, final iteration. So 1 0 1 0 means what? 1 0 means subtraction, right? AC minus BR, shift to AC. So this operation you are doing with AC plus BR plus 1, AC and the arithmetic shift right. This is the second operation. So this is the first operation, this is the second operation. So okay, just take this 1 1 1 1 0, what is BR bar plus 1? That is nothing but 0 1 0 0 1, right? 1 1 1 0 1 0 1, ignore the carry, right? So 0 1 0 1 1, right? 0. So count become 0, and you need to perform the, so count becomes 0, you need to so this is the first step, addition. You need to perform the shifting, right? So shifting, you do shifting 0, you write here. This is the second step, I am doing arithmetic right shift 0 0, okay? 1 1 1 0 1 0 1 1. Finally this is the result, right? This is the result 0 0 0. So this is 1, you can estimate here. So this is nothing but, right, 64, okay, 2 power 0 2 power 1 2 3 4 5 6, 2 power 6, 64 plus 32 plus 16 plus 8 4 plus 1, right? So this is, if you add all these things, this is nothing but 117. This is the product of, okay, minus 9, right? Product of minus 9 into minus 13, that is 117 in decimal, right? So this is what the Booth multiplication, Babu. Please go through it. Thank you very much.